Welcome to the Crazy Hat Chemist. So another video here on Thermochemistry Part 2. So here we go. Bam! So today we're talking about enthalpy calculations here today. We're going to give you two different enthalpy calculations, two different examples. So we're going to determine the change in enthalpy, that is the delta H naught, for the combustion of ethane. Ethane is C2H6, that's a gas, given the following thermodynamic data at 298.15 Kelvin. That's 25 degrees Celsius. By the way, you should be looking up in the back of your textbook. There should be an appendix of thermodynamic data. And this is just the necessary thermodynamic data from that table that I've extracted out of that. Or, of course, you can look in the Handbook of Chemistry and Physics, the CRC, and all this information is in there. So here we go. We've got a partial table of only what is necessary here for this particular problem. So you can see I've got two columns here. I got my species, and then I've got my delta H naught of formation in kilojoules per mole. Make sure that you take a close attention to the units here on the thermodynamic tables, because depending on what thermodynamic value it is, then the units will be different. Okay, so for oxygen, O2, that's a gas, that has a delta H naught of formation of 0 kilojoules per mole. For water, that's H2O, that's a liquid, has a delta H naught of formation at negative 285.8 kilojoules per mole. Now, a note, there is also in that same thermodynamic table water that is a gas. So make sure that you pay attention to the state of matter when you are looking at this table. So that, because some of the values are very close, but the state of matter does make a difference. And then we have our ethane at C2H6, that's a gas, at negative 84.7 kilojoules per mole for the change in enthalpy under standard conditions. And then we have carbon dioxide, that's a gas, and the delta H naught of formation for that is negative 393.5 kilojoules per mole. Now, this is very important because some thermodynamic tables do not include elements in their standard state. It just so happens that elements in their standard state, their delta H naught of formation is going to be 0. Oxygen might not be in your table. Why is it not in your table? Because it is an element in its standard state. And that is, oxygen is a diatomic molecule, okay, and it is a gas at 25 degrees Celsius and 1 atmosphere. So at standard state conditions, which is 25 degrees Celsius and 1 atmosphere, oxygen is a molecular compound that is diatomic, okay? And its delta H naught of formation is 0. I'm going to give you another couple of examples here. Osmium is a solid, as is iron a solid, and both of those are monoatomic. So at 25 degrees Celsius and 1 atmosphere of pressure, the delta H naught of formation for both osmium and iron are going to be 0. Whereas chlorine gas is diatomic, and at standard conditions, which is 25 degrees Celsius and 1 atmosphere, chlorine Cl2 would be 0 for the delta H naught of formation. So hopefully you got that. So elements in their standard state are 0 for the delta H naught of formation. Okay, so now the next thing that I want you to do is I want you to write the balanced equation for this reaction, that is the combustion of ethane, and then write that equation, balance it, write the states of matter, of course. Pause the video right now, and then when you're done, unpause that video so that you can get the answer. Well, hopefully you've balanced that equation with ethane, and here is that balanced equation. That is 2 moles of ethane plus 7 moles of oxygen produces 4 moles of carbon dioxide and 6 moles of water vapor. Water liquid, sorry. There's a delta above the arrow indicating that this is an exothermic reaction. All combustion reactions are exothermic. In fact, if you understand that concept, then you should understand that when you do the math on these combustion reactions, the change in enthalpy for the reaction is obviously going to be negative, which indicates that it's an exothermic reaction. Okay, but let's verify that and figure out what the numeric value is for the combustion of ethane. All right, so we're using this equation, that is delta H naught of the system is equal to the sum of the delta H naught of formation of the products minus the sum of the delta H naught of formation for the reactants. Notice that I've included those brackets around there, around the reactants, so that you don't screw up that negative sign. It's very important. Okay, now what I've done is I've plugged in those values from the products minus reactants and that thermodynamic data from the table. Okay, so delta H naught of the system is equal to 4 moles of carbon dioxide times the value for carbon dioxide, which is negative 393.5 kilojoules per mole, plus 6 moles of water times negative 285.8 kilojoules per mole. That's in brackets minus open brackets 2 moles of ethane, and that's at negative 84.7 kilojoules per mole, plus the 7 moles of oxygen at 0 kilojoules per mole. Now, you don't need to include the 7 moles of oxygen at 0 kilojoules per mole unless your professor likes that. Notice that I've closed off those brackets there. Now what you need to do is do the multiplication and then do the addition and take care of that minus sign very carefully. And then you should get a value for this overall here. And the delta H naught for the system, that is the combustion of ethane, is negative 3,119.4 kilojoules. Notice that the moles have canceled out. All these values have 1 decimal place in them, except for that of oxygen, which is just a flat-out 0. So the last operation is addition, and so therefore it will have 1 decimal place because it's the fewest number of decimal places with addition and subtraction. As I noted earlier, this is a combustion reaction, and you should have a negative value for the change in enthalpy, as indicated right here. Now I have a value. This negative value indicates that this is an exothermic reaction like all combustion reactions are. Now, if I were to place this value into that equation, it would be in that balanced equation, but it would be on the product side, and there would be a plus sign in front of it. So on the product side, I would have 4 moles of carbon dioxide gas, plus 6 moles of water liquid, plus 3,119.4 kilojoules. It would be on the product side since it's an exothermic reaction. All right, hopefully that worked out well for you. We got another problem here for you, so hold on. Bam, there's our other problem. Determine the change in enthalpy for the conversion of dinitrogen tetroxide to nitrogen dioxide, given the following thermodynamic data at 298.15 Kelvin, that's 25 degrees Celsius. Again, what I've done is I've taken your textbook, or really the handbook of chemistry and physics, and extracted out the important pertinent information for this reaction here. And I got nitrogen dioxide and dinitrogen tetroxide, the values of their enthalpy changes of delta H naught of formation in kilojoules per mole. Nitrogen dioxide is 33.85 kilojoules per mole, and dinitrogen tetroxide is 9.66 kilojoules per mole. I'm hoping that you come up with a balanced equation for this. You should come up with that on your own here. Bam! There it is. So that is N2O4. That's a gas. And these are equilibrium arrows because this is an equilibrium reaction. And it's 2NO2, sorry. 2NO2 gas. All right, now we're going to use this equation here that we've been stating all along, which is the delta H naught of the system is equal to the sum of the delta H naught of formation of the products minus brackets the sum of delta H naught of formation of the reactants. Remember, it's NPR, which is not products, reactants. The little 0 means at standard conditions. That's 25 degrees Celsius and 1 atmosphere. Okay, now we're going to plug in this thermodynamic data into that equation there. Remember, it's products minus reactants. We've got this delta H naught of the system is equal to 2 moles of NO2 times 33.85 kilojoules per mole minus 1 mole of N2O4 times 9.66 kilojoules per mole. We're going to plug all this information into our calculator, and then we're going to get a value for that. And that is delta H naught for the system is 58.04 kilojoules. Notice that this value here has 2 decimal places here because both of these values have 2 decimal places. If one of them had 3 decimal places and one of them had 2, then you would end up with 2 decimal places. That is the fewest number of decimal places. The last operation is addition. What does this value indicate? Well, this value indicates, since it is positive, this is an endothermic reaction. So where does the heat term belong? If I were to place the heat term back into my balanced equation, I would have on the reactant side 58.04 kilojoules plus N2O4. That would be on my reactant side. Hopefully that makes sense for you. Okay? That's a great video here. And of course, I'm the Crazy Hat Chemist, and I always got to end with a hat. And I got a great hat here for you. Okay? It's my favorite, well, not quite my favorite element, but it's my favorite soft drink. It is not rubidium like you might think it would be as a group 1 very reactive metal, but it is root beer! That's right. My favorite soft drink is root beer. If you like that video, give me a thumbs up. If you like all of my videos, subscribe to my channel and please pass it on to all your cool chemistry friends. And if you really like this stuff and you want more videos, then please donate to my website. You can do that, okay? And you can get yourself a sticker or maybe even a cool t-shirt. There's a cool back to that t-shirt, but oh, look at that. Great, great sticker, great t-shirt. My son designed them both. Give me a thumbs up and I'll see you next time. Bye for now.